let's talk about the unit circle. So on a unit circle, I'm going to explain to you why every point xy is actually a point sine theta, or sorry, cos theta, sine theta. And unit circle, what's the special property of the unit circle? Does anyone remember this from grade 11? Unit circle? No? So the unit circle is a special circle because it's the sort of smallest circle that you can have without going into decimals as your radius. So the unit circle has a radius of 1. So it's kind of a special triangle in that, or sorry, special circle in that sense. Caleb, can you shut the back door for us there? All right, so let's suppose we have some point on a circle, and this is always going to be a point xy. So we know any point anywhere on the Cartesian plane is a point with an x coordinate and a y coordinate. And we always measure a rotation from 0 degrees. So if we say that's 0 degrees, and we rotate a measurement, some measurement theta, over to connect that point to the origin. This will be our radius of the circle. This will be our x distance that we have to travel up to that point, and this will be our y distance that we have to travel up to this point. And that makes a right angle because x is horizontal and y is completely vertical. All right, so if we were to set up the trig ratios, which we practiced last year, if we were to set up the trig ratios in terms of x, y, and r here, we can use SOHCAHTOA, and theta will be our reference angle. So if theta is our reference angle, this will be adjacent, opposite, and this will be hypotenuse. So what is sine equal to in terms of x, y, and r? Athena? Y over r, because sine is opposite over hypotenuse, and here opposite is y, and hypotenuse is r. Okay, how about cos theta in terms of the x, y, and r sides here? Lexi? X over r, correct. And tan theta? Lucas?
Y over X.
Y over x. Okay, so with our special unit circle, we could go a step further here, and we could say in the unit circle, sine is equal to y over 1, because the unit circle has a radius of 1, which actually makes y equal to sine theta. Only in the unit circle, right? And similarly for cosine, because the radius of the unit circle is 1, x is actually equal here to cos of theta. So that's why every point xy is actually equal to cos of the angle times sine of the angle at that location. Again, only for the unit circle, right? So this must be with the unit circle with property that the radius is equal to 1. So this is an interesting little feature because using this whole circle that we created in our first lesson, there we go. Using this whole circle that we created in our very first lesson where we labeled all the radian values and all of that stuff with all the special values, we can actually now extend this and we can use this idea to figure out the x and y coordinates at any rotation for those special angles around the circle, and that's where this comes from. Okay, so we'll talk about this. I know it looks kind of crazy right now. But, so we've got our degree values in here. We're not really going to be using those as much, but might be just a good visual for you to see how they connect back to what we did in grade 11. And then we have now our new radian values around here. And we have some x, y coordinates at each of these points around the circle. So let's look at pi over 6, for instance. Pi over 6, what we proved above is that the point that's on the circle of radius 1, when we have pi over 6, should be equal to cos of pi over 6 and sine of pi over 6. So if we were to calculate, let's say, cos of pi over 6, we can use our special triangle. And our special triangle from the pi over 3, pi over 6 triangle is, whoops, actually those are supposed to be in the opposite spots, is 1, root 3, and 2. And we know that the cos of pi over 6, this will be adjacent, and this will be hypotenuse. Cos of pi over 6 is root 3 over 2. And sine of pi over 6 is 1 over 2. And so do you guys notice this should be the x-coordinate at this location, this should be the y-coordinate at this location, and we can see here this is the x, and this is the y at this location. And it continues around like that. So that's sort of where these points are being generated from. This is, we can even label it on here. This is cos of pi over 6, and this is sine of pi over 6. And similarly, I can get the xy coordinate on the unit circle at the point pi over 4, at the rotation of pi over 4, by doing cos of pi over 4 and sine of pi over 4 in order to get these two values. So why are these root 2 over 2? Well, this comes from the special triangle, the pi over 4 special triangle. Okay, 1, 1, and root 2. So if I were to set up the x and y coordinate at pi over 4, I would do cos of pi over 4, which is 1 over root 2, and sine of pi over 4, which is also 1 over root 2. So why are these labeled as root 2 over 2 and root 2 over 2 over here? Where does that come from? Nobody knows? So root 2 over 2 is equivalent to 1 over root 2, and the reason is that if we rationalize the denominator, so if I multiply by root 2 and root 2, I get root 2 over 2. So 1 over root 2 and root 2 over 2, that's actually the same thing. Okay? So it's just showing you the point with the rationalized version of the denominator, which is root 2 over 2. Okay? So those are equivalent. So that's why we have root 2 over 2 instead of 1 over root 2 for both of those values. Okay, so there's a couple things that you will notice about some of these points. The first thing is I want you guys to look around at all of the pi over 6s. What do you notice about the points that have pi over 6s here? The xy coordinates. All of these points. Esther? Yeah, they all have an x-coordinate of root 3 over 2 and a y-coordinate of 1 over 2, except some are positives and some are negatives. So why would just this x-coordinate here be negative in this quadrant? What do we know about x and y in this quadrant up here? Athena? Yeah, if I go this way on the x-axis, I'm going into the negative section. Evan, can you just take out the headphone there? I'm going into the negative section of the graph, right? And if I go up on the y-axis, I'm going into the positive section of the y-axis, right? So notice that all the y's are positive in this quadrant and all the x's are negative in this quadrant. That's why the cast rule is what it is, right? That's why if sine is y over r, sine must be positive in this quadrant because all the y's are positive in this quadrant, right? That's where the cast rule actually comes from, okay? And then similarly, you're going to notice that in this quadrant down here, all the x's and y's are negative because if I go left and down, that's positive, negative x's and negative y's. And then same thing, same idea with this quadrant. If I look at this quadrant, if I go right on the x-axis, all the x's are positive. If I go down on the y-axis, all the y's are negative. Okay, and then of course in the upper quadrant, the x's and y's are both positive, and that's why all trig ratios are positive in this quadrant. It's because x's and y's are all positive. Okay? So if I know these 3 points right here, I can actually fill out the whole rest of the unit circle, right? I just put negatives and positives in front of the things that need negatives and positives based on which quadrant they're in. Okay, so let's use this in action here. We'll see this used. This is sort of an alternate to what we did earlier today. This is like, if I know the unit circle, I can use this method instead of the method that we were just using in our previous lesson. So this says use the unit circle to determine all values of 3 pi over 4. So if I were to do sine of 3 pi over 4, I would actually simply just look at the y-coordinate because sine theta, cos theta, sine theta is the y-coordinate, cos theta is the x-coordinate. So if I locate 3 pi over 4, I'm actually just interested in the y-coordinate at this location. That's the sine of 3 pi over 4. So this is actually equal to, no work needed except setting up the unit circle. This is equal to root 2 over 2. Cos of 3 pi over 4 will be equal to the x-coordinate at this location. So the x-coordinate is negative root 2 over 2. So I will just say that equals negative root 2 over 2. Tan is equal to y over x. So if I wanted to set up tan, I would do the y-coordinate at this location over the x-coordinate at this location. I would get root 2 over 2 divided by negative root 2 over 2. What's anything divided by itself? Just 1. This one's a positive and negative though, so this will be negative 1, right? Okay, and then of course for the reciprocals, all I need to do is switch the signs for those values. So if I want to do cosecant, I'll do 2 over root 2. Secant, same thing, but negative, negative 2 over root 2. And cotangent, reciprocal of negative 1 is actually just negative 1. So we can just leave that one. Okay, and then for 7 pi over 6, I will look at that location now. X and y coordinates at that location will tell me the cos and sine. So here's 7 pi over 6 right here. So if I wanted to do the sine of 7 pi over 6, I'm just going to look at the y coordinate at that location. So it will be equal to negative 1/2. Cos of 7 pi over 6, I'll just look at the x-coordinate at that location. Negative root 3 over 2. Tan, I'm going to do the the y over the x. So I'll do negative 1 over 2 over negative root 3 over 2. To keep this as an exact value, I'm going to take this bottom fraction and flip and multiply. Okay, that's what we do when we divide two fractions. Take the bottom one, flip and multiply. So negative 2 over root 3. The 2's will cancel, and the negatives will cancel, and I'll just be left with 1 over root 3. Okay, and then similar to what we did above, we'll just take each of the reciprocals here. So cosecant 7 pi over 6, and just flip it. We'll get negative 2 over 1, which reduces to negative 2. And we'll do negative 2 over root 3. And then for cotangent, we will do root 3 over 1, which will reduce to root 3. So the deal is if I want to use the unit circle, I have to obviously understand how to set the unit circle up. But once you set this up, you can do lots of questions really quickly because you have all the values like pretty readily available versus doing the 4-step process that we talked about in our previous lesson, right? So this is a nice little unit circle that we can use to sort of help us calculate all these values much more quickly. But I can still do it the other method as well. Oscar?
Are we going to get the unit circle on the test?
No. So you have to know it if you want to use it. Okay, and you should know anyways, you should know how to fill out these angles because you'll need to know where to place them in radian value when you're working in radian value. Athena? You will have to use the unit circle for these values on the lines, but I will not tell you specifically you have to use the unit circle to calculate something like the sine of 5 pi over 6. Okay? Okay, so the second part of this is the values like 0, 2 pi, pi over 2, pi, and 3 pi over 2. We're just going to do these two right now. So I want to just explain to you where these all come from. Okay, so as a reminder, this is a unit circle with radius 1, right? So the radius is equal to 1. If I go 1 unit to the right on the x-axis, this point has to be the point 1, 0. Right? If we were just looking at a Cartesian plane and I went over 1 unit to the right, that's the point 1, 0. If I were to go up 1 unit on the y-axis, this is the y-intercept of 0, 1. Okay? Because I just went up 1 unit on the y-axis. Okay? Left 1 unit on the x-axis, this is the x-intercept, negative 1, 0. And then down 1 unit on the y-axis, that's the point negative 0, 1. And we can use these pretty easily to calculate sine, cos, and tan, or the reciprocals, by just using the x and y coordinates at these locations. So this is like a no calculator thing. So we're going to use the unit circle to determine the sine of 3 pi over 2. And just as a reminder, sine is equal to y over r. So we're going to look at what is the y location at the rotation of 3 pi over 2. Look at your unit circle here. So here's 3 pi over 2 right here. That's what I'm looking at. What's the y coordinate at that location? Negative 1 is the y coordinate. And of course, we know on the unit circle the radius is 1. So sine of 3 pi over 2, without using a calculator, is equal to negative 1. You can check on your calculator. If you plug in sine of 3 pi over 2, you should get negative 1. Okay? Let's just try one more here. What about, let's do tan of pi over 2. Okay? So just as a reminder, tan is equal to y over x. So on the unit circle, we're going to look up at pi over 2. What is the y and the x at this location? Carol? So it will be y over x, 1 over 0. And we know anything over 0 is actually undefined, right? So tan is actually undefined at this location. I'm just going to say undefined. Okay, so that's kind of the idea. I can also do it with the reciprocal ratios as well, right? So if sine is y over r, cosecant is going to be r over y. So you can just do that the same way. Okay, and then this one we sort of went over in our worksheet, but how would I evaluate something like cosecant of 1.5 on my calculator? How do I do that? We practice with cotangent on the worksheet, but Oscar?
You do 1 divided by sine.
Yeah, perfect. 1 over sine of 1.5, making sure you're in radian mode, so you guys can use your calculator for this one. Let me know what you get. Oliver, what'd you get?
1.0025.
Lexi, same thing? Okay, perfect. And that's just the ratio, so we'll just leave it at that. No unit of measurement needed there. Okay? The important thing, guys, if you don't want to, if you're kind of confused by the use of these points, that's fine. The important thing here, guys, is that you know, is that you understand these four things that I just explained, and that you could calculate that without a calculator if needed. So if I wanted to calculate cos of pi, I would do x over r, and I would get negative 1 over 1, and that would give me negative 1 for cos of pi. Okay? So that's kind of the idea. So you need to understand where these points are coming from, right? Okay, we're going to call it there today.